Hello students, welcome to the channel Statistica Hub. This is our lecture number 13 in the course SH201A, Probability Theory. So in this particular lecture, we are going to cover the geometric distribution, and it is again a very nice distribution and nice properties that we have to follow on. So let's start with the geometric distribution. So if I just go for like the same ideas going on, like we covered the Bernoulli distribution, the binomial distribution, the Poisson distribution. So in this one also you are having the similar concept that you are having the Bernoulli distribution. Okay. And we are going to make use of the Bernoulli distribution only. So in this particular part, you are just counting that, okay, you go for like, I can just give maybe one example. We can frame some example. Let's say you are going to play some maybe some kind of game. Okay. And the point is like, you have a very high urge to win the game. So you are going to play the game again and again, again and again, and you are going to stop playing the game once you win the game. Correct? So that is the setup. Like you're going to play until you win. So in this particular setup, if I say number of games that you play to win first. In this particular setup, I can go for maybe the first game. I may win, I may lose. So if you are winning, then you are going to stop that. Okay, I won the game. That's it. I'm happy. So in that particular part, you are going for like only one game. Okay. Now the point is you go for the first game, you lose it. You go for the second game, you win it. You stop at the second place, that okay, now I'm happy. In a similar sense, it can go to infinity. Like you may be playing the game again and again, again and again, again and again, and every time you're losing the game. So the point is, if I go for the definition, a geometric distribution models the number of trials until the first success in a sequence of independent Bernoulli trials. That means to say you are having n independent Bernoulli trials, you are having infinite Bernoulli trials, and you are going to play the game, or you are going to count the total number of trials that are required to get the first success. Okay. Now, in this particular part also, you have to go for the similar kind of thing that we are going for the first game and the second game. So they are independent of each other, and the probability of success, probability of winning the game, that remain the same. Okay. So that is the geometric distribution. Okay. So in this particular part, if I go for the probability function, so you can think about it very simply. So I go for like the possible values of x. So you can think that x can take value 1, 2, 3, and so on. Like it is roughly x is the number of trials required. So that means to say like you have to play the game for at least one time to win the game, correct? So it is not possible you don't play the game like at all and you are going to win, correct? So in this particular thing, the x can take value 1, it can be 2, it can be 3, and so on. Okay. Then if I go for probability that x is taking a value k, so we are having this idea that you are going to play the game for k number of time, and on a kth time you are winning the game. So we are having the first place, the second place, the third place, and so on. We are having the kth place. And in the kth place, you are going to win the game for the first time. All other time you are failing the game, you are losing the game, and so on. So we are having the failure k minus 1 times, and the success that is kth at the kth place. So this will be 1 minus p raised to the power k minus 1 into 3. That is the probability function. And in this particular part, the parametric space that will be like you denote x follows geometric distribution with the probability p. And in this part, the p will be in between 0 and 1. Okay, so we are having this idea about the geometric distribution. Okay. Now in this part, like the probability of success that can't be 0. Like if the probability of success is 0, then we are having this idea that there will be no success. Okay. So that is the idea, like the probability can't be 0. Okay. Moving ahead with this particular part. So if we move ahead, then yeah. Then again, we have to go for the property. So in the properties, if I go for the first property, the mean, so that will be the expectation. So expectation of x in this case, that will be 1 over p, and variance of x, that will be q over p square. Okay, that is the mean and the variance, and you have to memorize them. Like you'll be finding direct problems that are based on these type of things. That what is the mean, that what is the variance, and there will be certain problems that are very simple. Okay, this is the memoryless property that the geometric distribution follows a very particular property, that is the memoryless property. Okay, just go for the statement in this particular slide only, and in the coming slides, I will be covering up like more about the memoryless property. So we are having probability that x is greater than some m plus m, given that x is greater than n. You can think about this idea maybe the life cycle or something like this. Okay, uh, technically you are saying that when x is greater than n, that you are not getting the first success until the nth trial, and then it is saying that you are going for m more steps. Okay, this is like 1, 2, 3, 4, 5, 6. Let's say this is the nth place, and you are saying you are getting a success after the nth trial. Then the probability that after n you require m more steps, 1, 2, 3, and so on, maybe n plus n. They are saying you are going to get success anywhere at this place. Okay, so that will be simply coming out to be probability x is greater than n. So the idea behind this thing is memoryless property, like whatever has happened earlier, you can ignore that thing and you can start from this point that, okay, take the n to be 0 and you go for like 1, 2, and so on, finally m. So that's the idea of memoryless property. We are going to cover this like in some detailed format, but for now, just take this is the intake about the memoryless property. Okay. Then if you have to go for the expected value, so simply go for like summation k probability x equal to k and k running from 0 to infinity. You just go for like the infinite summation of the series and it will be coming out to be 1 over p. Okay. Similarly, you can go for the variance of x, expand the formula, you will be getting q over p square. Okay. Moving ahead, then we are having the moment generating function. So that will be your mxt summation k running from 1 to infinity e raised to the power t k probability x equal to k. Again, summation and so on. And if you just go for the derivation of this particular thing, it will be coming out to be p e raised to the power t over 1 minus q e raised to the power t. Okay. And in this particular setup, we are having the t that will be less than minus ln 1 minus. So there is some condition on the t in this particular part. And this is like you have to memorize what is the mean, what is the variance, and what is the mxt. Okay. Apart from this, like I didn't go for any particular derivation in this particular slide. So I will just leave that on the reader. So you have to go for the derivation for the mxt in this particular part. Just follow the same steps like whatever we just covered in the earlier two slides, or maybe the earlier two lectures. You just follow the same thing, writing the things, expanding the things, doing the summation. That's it. Okay. And at the end, you need to memorize that the mean is 1 over p, the variance is q over p square, and the mxt is p e raised to the power t over 1 minus q e raised to the power t. So these are some of the things that you have to memorize always. Okay. Then we are having certain examples. So you can go for number of coin flips until you are getting the first head. Okay. That means to say you are going to flip the coin again and again. Once you get the head, you are like, okay, done. The second example, number of trials to get the first defective item in a quality control process. Okay. So that is the number of trials that you may be requiring to get the first defective item. Like you may not be getting any success, you may not be getting any defective item, but you just keep on trying once you get the defective item. Okay. Example number 3, number of times rolling a die until the 6 appear. Again, a similar example. Okay. Now we are having some problem that you can see over. So we are having like if the probability of success in a single trial P is given to be 0.2. Okay. And what is the probability that the first success occurs on the fourth trial? That means to say you are having X that follows some geometric distribution with probability of success 0.2. And then they are saying you have to calculate probability that x equal to 4. We already have the formula q raised to the power n, that is x minus 1 into p. So I will be getting 0.8 raised to the power 3 into 0.2. Once you solve it, you are going to get 0.1024. Okay, so that is a very simple example on like the geometric distribution. Okay, moving ahead. Now we are having some applications that we already covered a little bit. So you go for like modeling number of trials until the first success in various fields. You can go for any particular field. Maybe the students who are appearing for some particular entrance exam. So there are certain exams in which they are going to have like maybe there is no age limit. Just consider one example. So in that particular part, you may be appearing for that particular exam again and again, and you are going to appear till you get the success. Correct? So that can be modeled using the geometric distribution. Okay, it is used in reliability engineering, quality control, natural sciences. Again, the number of phone calls until you are getting the first connection. So this can be taken up maybe in the sales marketing, telemarketing, or something like that. Okay, so in that part, like the company executives, they are making a lot of calls like every minute. Maybe some loan company, maybe some credit card company. So they are making a lot of calls to like every individual. So once a connection is set, they have to make a call. The proper conversation will be there. So the idea is the number of press or the number of phone calls that they require to get the first successful client, that can be modeled using the geometric distribution. So this was some basic idea about the geometric distribution, the properties of the geometric distribution. So out of the class of different properties of the geometric distribution, the most important one is the memoryless. So let's come to that part. Okay. So let's go. What is the meaning of memoryless property? So the memoryless property states that the probability of success after a certain number of failures is independent of the number of failures that have already occurred. Okay, you can think about this case that maybe I have appeared for some particular exam two number of time and I didn't get the success. So if I go for maybe the third time, is that depending on the previous one? So technically, no. If you go for like any real world, so that is not depending on the previous one. So that is the most generic example that we can think over. So this is the memoryless property. So it is saying that probability that x is greater than n plus m. That means to say to get the first success, you are having n plus m number of failures, given that you already had n number of failures. So that is completely independent that after the time slot, maybe the n, after the cutoff point n, there are more m number of failures. So that is the major idea. That's how we see the memoryless property. So the probability that x is greater than n plus m given x greater than n, that will be probability x greater than m. Let's try to see like how this is coming up. So we already have the basic formula like the probability formula and everything. So let's try to see is that holding true. So I had to write this particular part. So we have the probability of a given b. So I hope you remember from the earlier lectures. This will be probability of A and B over probability of B. Okay, go for this one. So that will be probability x greater than n plus m and x greater than n over probability x greater than n. Correct? Now, in this particular part, you can simply think about this setup. Let's say this is the n, this is the point m plus n. So that means to say these are the n steps, these are the m steps, and they are saying it is greater than this and greater than this. So we're left with only this particular part. So that is probability x greater than n plus m over probability x greater than n. Okay. We simply have to calculate this particular part. So you can simply write that will be 1 minus probability x less than equal to n plus m over probability 1 minus probability x less than equal to n. So if you just solve this thing, maybe I have given that proper derivation on the next page. Yeah. So you can simply think that we are going to get something like this. And if you just solve this part, probability x greater than n, that will be 1 minus p raised to the power n. And if you go for probability x greater than n plus m, that will be 1 minus p raised to the power n plus m. You take the ratio, that will be coming out to be 1 minus p raised to the power n. That is the probability x greater than m. So you can memorize one thing, that this is the CDF formula also that we are getting, that if x is following some geometric distribution with probability p, then the CDF, that is probability x less than equal to some m, that will be coming out to be 1 minus p raised to the power n. So just remember this part also, that the CDF for the geometric distribution, that will be looking like this. So these are the properties of the this is the most important property, the memoryless property in the context of geometric distribution. Okay, moving ahead, then we are having some example. So they are saying that suppose that the probability of getting a head in a flip of the coin, that is 0.5. Now let x is the number of flips that are required until you get the first head. So again, that is an example of the geometric distribution. Okay, now the question is, given that the first three flips were tail, that means to say you are already having that x is greater than 3. What is the probability that it takes another two flips? So probability x is greater than 5 given that x is greater than 3. So that will be probability x is greater than 2, right? Because the 5 that can be written like 3 plus 2. And we can convert something like this. That will be coming out to be 1 minus 2, 0.25. That is the probability. So this is a most easy or the most simple example based on the memoryless property of the geometric distribution. Okay. Another example that we are having. So in this particular process, the probability of producing a defective item is with probability 0.1. So we are having X that follow geometric with probability 0.1. Okay. Let X be the number of items inspected until the first defective item was found. Okay. So we are going for like the X that is counting number of trials that are required to get the first success. If I just say success being the first defective item. Okay. Now in this particular part, they are saying that if the first 5 items are defective, are non-defective, what is the probability that it takes next 3 items are also not defective? Also very simple, like probability X is greater than 5 plus 3, given X is greater than 5. That is simply probability X is greater than 3, and I'm going to get 1 minus 0.1 raised to the power 3. Just remember this property that if you are saying that X that follows some geometric with P, then probability X is greater than some number K, that will be 1 minus P, what I'm writing, 1 minus P raised to the power K, and probability X is less than equal to K, that will be 1 minus P raised to the power K. Just remember this CD form that will be required. Okay, we have another example. So in this example, the probability of successful phone call, that is 0.3, and let X be the number of attempts until the first success is gained. Okay, so we are again having the X that is following some geometry with probability 0.3. Given that it takes first 2 attempts failed, what is the probability that it takes at least 4 more attempts? So probability X is at least 4 more attempts after the first 2 fails. So greater than 6 given X is greater than 2. So that is coming out to be probability X is greater than 4. The difference between them, that is 1 minus 0.3 raised to the power 4, that is 0.2401. The same. Okay, so these are some of the examples that are based on the most generic form, like the memoryless property. Okay, so this is like very important property. Like if you go for maybe the Markov chain on that particular part, then you may be finding like there are waiting times or something like that. So in that particular part, that will be required. If you go for any survival analysis, in that one also it will be required. So a lot of things, this property is like holding a very important part. Okay. Then this is just a summary. So the memoryless property is a unique characteristic or the feature of the geometric distribution. So that means to say like this particular property in the case of like discrete random variables, only the geometric distribution will be following the memoryless property. Okay, so only the geometric distribution follows memoryless property in the class of discrete random variables. So that means to say it is like a unique property that is being held. Okay, we have just covered some about the definitions, some properties, some examples. Okay, and this is holding a lot of importance in the context of like statistical knowledge or maybe in some sort of statistical analysis. Okay, so this was all about the lecture number 13, the geometric distribution. I hope you are able to understand. And in this particular slide, I didn't go over like a lot of derivation. So whatever derivation that we skipped, so I hope that you are going to solve them like on your own. You have to go for the proper derivation and make your proper notes if you are following these lectures. Okay, so this was all about the geometric distribution. That's all. Thank you. Bye.